Thanks, Manfred. Thanks for the organizers for this invitation. And I'll talk about the DUNE experiment that is one of the most ambitious projects for the next coming years. And as a matter of fact, it's not a project anymore. We have already started to build the experiment with the excavations at the far side. And so this is the outline of my talk. It's why neutrinos, why it's so important to study the behavior of neutrinos in the face of features of the standard model. Then I will move to the concept of the experiment and few technical details. And then I move to neutrino oscillations, the baseline, and the capabilities of the experiment to study these important features of neutrino oscillations. Then I will do the same for the astrophysical studies of supernova. And then I will move to the conclusions. So this is a very brief description of the DUNE's mission and concept. So the main reasons talking about physics are this set of questions that what is the origin of the matter and antimatter asymmetry in the universe. Essentially is why we observe this huge imbalance of matter and antimatter, since in the beginning of the universe it should be half and half. And what are the fundamental underlying symmetries of the universe? Because if it's possible to connect the mass pattern and the mixing patterns in the lepton sector with the quark sector, it can unveil to us hidden symmetries in the standard model. Another question, if is there a grand unifying theory of the universe that can be explored through the channel of observing Bionumber violation? And also, how do a supernova explode? So it can bring us new lights on astrophysics and also informations on the neutrino particle itself. So to do so, this is the concept and the layout of the experiment, where a very intense beam of neutrinos will be produced at FERMILAB, and just downstream of the beam, we have a complex of four different near detectors to measure the unoscillated flux and constrain also the flux of particles that goes underground from 1,300 kilometers up to the far side. It's an underground laboratory in which we have a very large liquid argon time projection chamber. So we expected to work in the particle and antiparticle mode in 50% of the time. So this is the recent picture of the collaboration meeting. Up to now, we have almost 1,200 collaborators from 188 institutions in 34 different countries. So this is the concept, in just one slide, the concept of the technology chosen by for the Far Detector. It's a liquid argon time projection chamber, and the principle is when you have charged particles crossing the liquid argon, it will produce photons and also ionized electrons that are accelerated through a very intense electric field towards a mesh of wires. It's an anode. This is the anode plane. And the impact point here will give the one of two coordinates, and the time between the point of the production point and the collection wires will provide the third coordinate that enable us to make a very clear 3D reconstruction of the event. So this is a very challenging technology that it's already proven by some previous detectors, just like Icarus and the Proto-DUNE that has been working since 2 years ago, more or less, at CERN. And also we have an alternative technology for the next modules of DUNE, that it's the dual-phase liquid argon time projection chamber that is pretty much similar what was described by Elena in her talk for the xenon dark matter experiment. And the difference is because we have a gas phase in the top of the liquid phase that can amplify the signal, and the coordinates it's given by the impact point of the electrons accelerated through a large electron multiplier. Okay, so this is a picture of one of the modules, because DUNE at the end of the construction will be made by 4 of these guys, and this is the technology for the cryostat was chosen by a very known and technology used in ships to transport liquefied gas all around the world, and it's a membrane cryostat. So the main component is this guy that is made from INVAR, that is material that has a very small expansion coefficient, so it's very stable against changes in the temperature. And outside the cryostat, we have this iron structure, this steel structure to sustain and keep all the detector working. So this is an internal view of the cross-section of the time projection chamber. So along the width of the detector, we will have 3 anode planes interleaved by 2 cathode planes. So the beam goes in that direction, along this direction that is parallel to the planes. And this is a picture that we had in Proto-DUNE that we can see in the walls, the membrane of the cryostat. And here is one of the mesh panels in which it's possible to see these horizontal bars that are components of the photon detection system. About the Near Detector. The Near Detector in the near side, as a matter of fact, it's composed by 4 different detectors with different capabilities. So the first one is the Argon cube, that is a reduced version of the Far Detector that we can see here. So this is the beam direction that is shown here, the beam pipe. It's rotated, these 2 views. So the Argon detector is this one, the first one in the direction of the beam. The second one is the multipurpose detector, and the third one that can measure also the content of muons in the beam flux. And the third one is the sand detector that it's used to monitor the beam intensity. So one important feature is that, as a matter of fact, the 4th detector is a combination of the first 2, the liquid argon and MPD, that can move along the near side hall for about 30 meters. And the purpose of this ability is to deconvolve the spectrum and the cross-section with the response functions of the detectors. So this can be applied afterwards in analysis of the Far Detector to make it more clear the physics of the signal and disentangle from the experimental issues. So let's talk a little bit about neutrino oscillations. Everyone knows that the flavor and the mass eigenstates does not coincide, so the connection can be made by the PMNS matrix. And this is a factorized version of the PMNS matrix that simply 3 successive rotations over the basis And the main parameters are the cosinus and sinus of the rotation angles. And it's important to see that we have an overall CP violation phase that is one of the main targets of DUNE. So just a few words about the CPT invariance that was tested in the MINUS experiment, and no evidence of the CPT invariance was found. So it leads to that in the lepton sector, asymmetries in neutrino versus antineutrinos arising from can be observed by the measurement of the CP violation, and in this case, in the appearance mode, okay? So this is if you can take the inner product of the states, you can calculate the conversion probability from nu mu to nu e, and 1 minus this guy gives you the survival probability. But since we are interested in the appearance mode, the probability can be split in 4 terms, and this one is the responsible to show the behavior or the intensity of CP violation, because you change sign in the sinus term in this probability. So what we do know? We know the ordering of the first line of the PMS matrix. We know the delta M square from in the 2-1 mass eigenstates, but we don't know the signal of delta M square in the atmospheric sector. We know quite well the values of the mixing angles, and what needs to be determined is the sign of delta M32 square. That means that we don't know if the third eigenstate is heavier, mass eigenstate is heavier than the second and the first one, or if you have the inverted hierarchy in which the third mass eigenstate is lighter than the 1 and 2. And so this has a big impact on the probability, the oscillation probability. Another important question is in what octant we have the mixing between the 2 and 3 mass eigenstates, because if you have the value is quite close to 45 degrees, but we don't know the octant. And the octant, the octant can give you, it's embedded in the 2 matrix and the Kobayashi-Maskawa matrix and the PMNS. There is a factor that takes into account the octant, and then we can, if we have a maximal mixing, this shows a symmetry connecting the quark and the leptons description in the standard model. Another feature is the CP violation that can precede the baryon violation, the baryon number violation, the first instance of the universe, and this can be assessed by observation of the CP violation into neutrino oscillations. So this is just to show you the difference in particles and appearance of particles and antiparticles. That is the degree, the different degree of suppression in the flux in the energy range of the neutrino beam that is shot to DUNE. So this is a plot that shows you Monte Carlo, a complete Monte Carlo simulation and reconstruction chain for normal hierarchy, particle and antiparticle in the disappearance spectra. There are different behaviors. So here you can see some of the important backgrounds that you should take into account. And this is the same, but for the appearance spectra and normal and inverted hierarchy. And these are the possible extreme values of delta CP violation. The same can apply here. The proportion of these error bands due to the CP violation can be applied here, where you can see very different behaviors. The same apply for the reconstructed antiparticles that you can see we have inverted behavior. And so what is the strategy? The strategy is to use observations from the same experiment in the particle, anti-particle mode, and put the constraints from observed, measured at the Near Detector, and do a simultaneous and global fit of each one of different spectrums, and then extract the oscillation parameters. And for the sensitivities, here we can see this is the mass hierarchy sensitivity. This is for a very favorable value of delta CP violation, showing that we can reach 5 sigma of significance in 1 year of exposure. And this green band shows the 100% of different values of delta CP. So in 2.5 years, it's possible to reach a very significant discrimination of the mass ordering. So the same applies. It's more or less the same plot from here, but with another vision, that this is all the possible values of delta CP violation. This is for a normal hierarchy, for an inverted hierarchy, but for 7 and 10 years of exposure. And then you can see that we can reach a definite definition for the measurement of the mass hierarchy. So the same rationale applies here, but now it's for the measurements of the CP violation, where you can see here, for the most favorable case, we can reach something between 3 and 5 sigmas in 7 years of exposure. And here are the plots from the values, from all possible values in normal and inverted hierarchy of the delta CP violation. And we can reach a very good sensitivity for 3 to 5 sigmas in 7 or and enhance the sensitivity in 10 years of measurements. So this is the sensitivity to the theta to 3 octant, and this is the plot for orange and green. It's for 10 years and 15 years respectively, and we can see that we can reach a very good discrimination in the time foreseen for the DUNE operation. It is interesting to note that as far as time goes by, we can remove the degeneracies, increasing the statistics towards to pinpoint the values of the sinus square of theta to 3. So let's move to supernova detection in just one slide. It's from the theoretical point of view, the mechanism of supernova explosion is large, massive stars with mass larger than 8 solar masses can form an iron core, and then the iron core, the successive burning of silicon can add more and more mass to the iron core, and when it reaches the Chandrasekhar mass, the gravitation cannot be counterbalanced anymore. Then we have the crunch, and during the crunch we can have a phase transition between the degenerated gas of degenerated gas of electrons to a degenerated gas of nucleons, and then the core stiffs, and the matter, the infalling matter, bounces and invert the movement out towards the star. Okay, so these are the 3 main phases in which we can see the different behavior of the different flavors of neutrinos that are escaping from the core. So this is the very first phase of the supernova collapse, with a strong emission of electron neutrinos that signalize the first phase where electrons are captured by the protons and leaving a large number of neutrons inside of the star. So then we have the accretion phase during the phase that the infalling matter is still occurring. And then we have the explosion, and look at the different time scales. And then we have almost exponential cooling with the almost the same flux for different flavors of neutrinos. So this is just to show you the shape of expected neutrino emission, that it's basically a quasi-thermal distribution, and the temperature of the neutrino sphere is proportional to the average energy. That is one of these parameters of the analytical expression for the spectrum. And alpha here is the pinching parameter that shows the deviations from the thermal spectrum. So one of the most important features of DUNE is the ability to detect neutrinos from supernova in 4 different channels. This is the main one. And I should emphasize that the sensitivity for the electron neutrino flavor. And combining the different behavior or the different response of the detector for the 4 different channels, we can have a more detailed information on the spectrum. So this is the time integrated spectrum with the number of the total number of events distributed in energy, and this is the signal evolution in time. Is the counting rate in time that it's possible to see that different from other detectors that are sensitive to the inverse beta decay, the ability of DUNE to tag the electron neutrino events give us a very interesting feature to observe the neutronization burst. And okay, so this is the total number of events expected in function as a independence of the distance to supernova. So this is the galaxy edge, this is the Large Magellanic Cloud, and this is the Andromeda galaxy. And you can see that the green band is just for the first module, and the red band is for the complete detector. And we expect thousands of events in the representative distance that it's quite good statistics if you remember that we had only 20 events in the first supernova observation. So the study of features of neutrino spectra in principle should be a very nice feature of DUNE. So apart from the standard scenario for supernovae, one can see that if we include the collective effects that occur inside the neutrino sphere, there could be a dramatic change in the time evolution of the spectra. And since we expected a large number of events, it's possible in principle to observe this kind of effect of collective effects that it's very different from the swap between flavors due to the MSW effects that occurs outside the neutrino sphere. So about Bionumber violation and the possibility to study the grand unification theories, DUNE has a very special capability to detect the proton decay in this channel. So it can be somehow it can be used as a complementary measurement from, let's say, all the other channels that can be observed in the super K or hyper K or whatever. And there is another interesting interaction that is the neutron to anti-neutron oscillation that has a very clear signature that it's spherical spray of hadrons with total energy around 2 times the mass of the neutron. And so the equivalent sensitivity is around to 5.5 to 10 to the 8 seconds, 9% of confidence level. So we can see that DUNE has a multi-topic physics list apart from the oscillation program due to these features of the detector. And then we can study Bionumber violation. It's also possible, I didn't mention here, but it's also possible to test and to probe light dark matter in the Near Detector, and also sterile neutrinos and but constraints on non-standard interactions, non-unitarity of the mixing matrix, and who knows, study CPT violation in neutrino oscillations. So this is the DUNE timeline, and we are here. So the prototypes had running successfully at CERN. The first module installation should begin in a couple of years, and the excavations, it's already started in the far side, and it's important to mention that when the first module is ready, but the beam is not ready, it's possible to explore physics, non-beam physics, just like oscillations on the atmospheric sector, supernova bursts, solar neutrinos, Bionumber, and whatever. And then in 2026, we started the measurements with the beam. So conclusions, we have a very capable detector with this important feature of multi-technology in the Near Detector that will help to constrain very hard the uncertainties in the flux and the spectrum of the oscillated spectrum in the Far Detector. So we are able to solve the neutrino mass hierarchy and the CP violation. And also we have the capability to explore non-beam physics. And so the future is very promising. So thanks to everyone for the attention.